Okay, this is going to be the second clips for using the consistent deformation method to analyze the structure. And we are concentrated on the beam for this example. And you may see this beam have the pin support at A, roller support at B, and also the roller support at C. This beam has four unknown, right? It has four unknown. A sub B, A sub Y, A sub X, B sub Y, and the C sub Y. And it has three equation of equilibrium with one free body diagram. So this beam gonna have degree of indeterminacy of 1. By using the consistent deformation method, that means we're going to set 1 for the redundant force. Okay, and typically for this kind of beam, we will use the B sub Y. Why? Because when we select B sub Y, the beam will change to the simple beam. Okay, so we are going to determine the deflection of the beam easier. And after we use this consistent deformation to determine the B sub Y, we will determine also reaction. Okay, A sub X, A sub Y, and C sub Y. And then we can draw the shear diagram and moment diagram of the beam. We also use the moment diagram and the support to draw the elastic curve. And the last, they ask us to determine the vertical deflection at point D. Okay, we may imagine this one. We're going to have a kind of elastic curve, something like this. This is just a draft, and we don't know the inflection point or the detail of this structure yet. But as far as we're concerned, this is going to be theta sub C. This is going to be theta sub A. And this is going to be the theta sub B. And they ask us to determine the delta D is here. And at D, they also have theta sub D also. Okay? Okay. Let us start. Let's set B sub Y as the redundant. When you set B sub Y as the redundant, it's going to produce this one as the B sub Y is going to be here as the redundant, and then the beam will be separated into two cases based on the principle of superposition. One is subjected to the applied loading. We call this is primary beam. Okay, and another one will subjected to the B sub Y. And this is going to be another beam. So this beam will equal to, by the principle of superposition, primary beam plus this beam. And what we have is the deformation. We are going to concentrate on the deformation or the deflection at B. So next, this one is the delta sub B. And this one is going to be F sub BB, F deflection due to the point load at B, okay, at B due to the load applied at B. The first B is at B. The second B is the load applied at B, okay. We use F because the deflection due to the 1 unit load. So if this one is the B sub Y, so the total gonna have just B sub Y here. And then what we have is the deflection here is going to be 0. And now what is positive? So the delta B is positive. And this one going to be the negative because it's going to be upward. Okay, so our index is going to be the first one, the point of the deflection. And the second one, the point of applied force. And now we have this equation. And then the next step, first one, we analyze the problem. Okay, we set up the lindens. The second one, we determine the compatibility condition of the beam by considering the deformation of the beam. And the third one, we're going to determine the relationship between the deflection and the force. Okay, so now we go back to the previous chapter. We can determine the deflection delta B and F sub BB by various methods, such as the double integration, the moment area, the conjugate beam, the unit load method, or even the classical theorem. Okay, but for this one, we have the table. Okay, this one for the beam and this one for the deflection. Okay, curve deflection equation. This one equation. We have this one and this one deflection at x. Okay, this one the deflection as a given location, such as at x equal to L over 2. This is deflection equation at specific okay location. Okay, and what we have is compare this picture with this one is kind of the minor reflection between them. And if you consider this one, we have the L over 2 and L over 2. So this means it's going to be L over 2 is 6 meter and 6 meter, and the total length L of this beam, they are going to be 12 meter. And what next do we have? We have the W of 2 kilonewton per meter. And then what we are considering is the deflection occur here. Okay, it's occur at the middle. So the deflection at the middle can determine from this equation. Okay, if you set x equal to L over 2. And also for this one, if you set x equal to L over 2. And no matter the force on the left and the force on the right, but since you determine the deflection at the middle span, so you can use this equation directly, okay, to determine the deflection at the center of the beam. If you put the L over 2 into this equation or these two equations, you will arrive at the result of the equation in the form of 5WL power 4 divided by 768, okay, EI. And what we have, should know that although W is placed in the opposite, okay, of the one in the table, you can use this because we are going to determine the midspan deflection, which are going to be equal no matter the force is on the left and on the right. That is special case. Okay, and then W is going to be 2 kilonewton per meter. L is 12 meter. And then you get the result of this of 270 divided by EI and downward direction. Okay. Next, the same picture still apply for this problem, but for this one, you're going to have the A equal to L over 2 and the B also equal to L over 2, which is going to be 6 meter. Okay, by setting this, that means the B is going to be 6 meter. The L is going to be 12 meter. The deflection occur at this position, so X is going to be 6 meter. So put the X is going to be 6 meter. So if you bring that equation, you set the force P dot P equal to 1. Set the force P equal to 1.0. And then you substitute BXL into the equation. Okay, BX, okay, that is going to be x is going to be equal to a also. This is going to be the a. Okay, and this is going to be the b, 6 meter. So we have everything putting into your equation. You got it, 36 divided by EI. Okay, and now you have this by putting 270 and then divided by 36. You get this for 7.5 kilonewton. Then you get the redundant force of 7.5 kilonewton. Okay, and then you draw the free body diagram. Summation of x sub x equal to 0, a sub x equal to 0. If you prefer, you may summation the moment about c equal to 0. Okay, and then you're going to determine a sub y. So the rotation here is positive. The a sub y gonna time the whole length from a, b, and c. That is going to be 12. And it's going to pass this one 7.5. That is gonna time 6 meter. And this one have the resultant of 2 times 6, which is 12. And this one gonna rotate in this direction, unlike this one. So it's going to be in opposite. So it's 12 times, this one is 3, 12 times 3. So you get this a sub y equal to, this is going to be 36, right? And 7.5 times 6 is going to be 5 times 6, it's going to be 45. So it's going to be take the opposite direction of equal, so minus 45 and divided by 12. So you get this going to be minus of what? Minus of 9 divided by 12. Okay, that is going to be minus 7.75 kilonewton. So the a sub y is not in this direction. The a sub y going to be in opposite direction, and is equal to 0.75. Okay, and now you get the summation of f sub y equal to 0, and upward is positive. So your c sub y is here, c sub y plus 7.5 and then minus 0.75, and then that is going to be equal to 12. Okay, equal to 12. So your c sub y going to be 12.75 minus 7.5. So what is going to be 12.75 minus 7.5? It's going to be 5.25. So your c sub y is going to be 5.25 kilonewton. And then you get it for 5.25 kilonewton. Okay, that is the result that we have from using the equation of equilibrium to determine it. Now we are ready to draw the shear diagram. We put this as the horizontal direction, and this one is going to be the V kilonewton, and okay, this one going to be x meter. And when you draw this, first dv by dx equal to minus w by the graphical method. Okay, second you draw the scale dv equal to minus w dx, and if you integrate it from a to b, integrate it from a to b, so we have v sub b minus v sub a equal to the integration minus of the area. Okay, area under w between a to b. Okay, then the third one we have what? If we have the upward force, third one we have upward force P, delta V is positive. So downward force P, delta V is negative. Now we start by drawing this. We come to point A, and then we have this one downward for 0.75. So this is mean is downward. Okay, the delta V is negative, so it's going to be downwards like this. So it's going to be minus 0.75. And W is 0. So we come here, the dV by dx is equal to 0. So it's going to be all 0. Now, we have the upward force. Okay, so upward force delta V is positive, so it's going to be what? It's going to be plus 7.5 minus 0.75, and then you get this equal to 6.75. And now your W is this, so the dV by dx going to be minus 2, so it's going to be downwards like this. Okay, and since this one is up like this, it's going to be up like this. So this one going to minus 5.25 kilonewton, if you know that. But if you would know that, this is going to be V sub C minus V sub C is here. Minus here, minus 6.75. And then it's going to equal to this one, the area, minus of 2 times 6 minus 12. So V sub C is minus 12 plus 6.75. So you got this of minus 5.25. Okay, and then you got this minus 5.25, and then it's close to be like this. Okay, the important is the point of zero shear. This is the point of zero shear. This is going to produce the maximum moment between B and C. Can you determine the distance here of x? Sure. For the similar, from the triangle of this is 6.75 divided by x. 6.75 divided by x. So the slope is going to be this. Don't need to take the negative. This is going to be 2. So your x is going to be 6.75 divided by 2. 6.75 divided by 2 is going to be 3 point something. 6.75 divided by 2, 3.375. So you get this one for 3.375 meter. Okay. Now we go to the next step to determine the moment diagram. We have what? dm by dx equal to v, and then for the second, we dm equal to v dx, and then we do the integration from a to b. Integration from a to b. So we get this one of what? Of m sub b minus m sub a, and then it's equal to the integration of this, the area of v diagram between a to b, like this. Okay, and the third one, that's we don't use in this one. The third, we're talking about the moment, the clockwise moment. Gonna make delta m is positive, and the counterclockwise making delta m negative. And if there is no moment at A as the pin and at C at the roller, so the moment at A and C gonna have 0 value. So this is gonna be 0, and this is gonna be 0. This is gonna be x meter. Okay, and what we have is the axis here. Okay, axis here gonna be m kilonewton meter. Now we draw the moment diagram, we see the shear diagram. We draw the shear diagram, we see the problem. Okay, so now we have this shear. So the slope here, the slope from this to this portion is gonna be dm by dx gonna be minus 0.75. So you got this, that's 0.75. And what is the value of this coming into this one? M sub b, m sub here, m sub b, m sub b minus m sub a. Here is 0. It's going to be equal to the area under shear diagram between A and B. So that is going to be equal to minus 0.75 and time 6. Okay, 6 times 0.75 is going to be minus 4.5. So this is going to be minus 4.5 kilonewton meter. Okay, and then the shear change to 6.75 here. So the slope here is up. Okay, and then over here shear is 0. The dm by dx gonna be 0. So over here the slope is 0. Over here the slope is plus 7.75, 6.75. So the graph supposed to be something like this. And what is the moment here? We don't know. Yes, moment here minus. Moment here minus what? Minus this one minus of minus 7.5. Okay, and then it's equal to the area between this equal to 1/2 of what? Of 3.375. Okay, and times 6.75. Then you put it into the number. You got the m of what? Of this one. Take this one out. Okay, this is slope equal to 0. You get this for 6.891. Okay, that is going to be the value of the moment at this point, 6.891. And now this is 0, but you got to suspect the slope here. The dm by dx here gonna be this one. Okay, minus 5.25. And then the curve is going to be coming into this way. So this is going to be the result of the moment diagram. And also this is important one. This is point of 0 moment, because this is the point of 0 moment. The curve will change. This is positive. This is upward. This is downward concave, upward concave. So the elastic curve, since this is pin, this is roller, okay, and this is upward. Sorry, this is downward, and this is upward. So this is going to be upward, and this is coming to up with what? With the inflection point, and then this is concave down. Okay, it's going to be concave downwards like this, and it hit this. This is going to be the inflection point. Inflection point. Okay, this inflection point, that is the point that you change the moment between the positive and the negative. And also it's important when you putting the reinforcement into the beam. Okay, for example, for this one, if you like to put the reinforcement, let me put it in green. So you got to put for the positive moment, you got to put this one like this. Okay, that is for positive moment. And this one, you got to put this one, and it's going to be beyond the inflection point a little bit to the making the development length enough for the steel and the concrete. Okay, that is elastic curve and the reinforcement pattern. If you like to do this, when we sketch the elastic curve, considering the support condition and moment diagram, we got that. We got the curve as shown here. And next, we're going to determine the deflection at point D by using the conjugate beam. That means we are going to determine m sub d palm. And again, this is going to be what? The same as before. External pin and external roller gonna have the same between the real beam and the conjugate beam. The internal roller will change to the internal hinge. So this one gonna be the internal hinge, and then the direction of the elastic weight gonna be come out of the beam. Okay, if positive, elastic weight upward. Negative, elastic weight just downward. And then what we have is we are going to find the moment here. Okay, but before we can determine, if you have this one and then you have this one, elastic weight of this. Okay, you're going to determine d palm here, find the moment m sub d palm here. You gonna determine this one a sub y palm. That means you're going to determine the a sub y palm. How do you determine the a sub y palm? That means you got to consider this portion of the beam. This is the internal hinge. Okay, this internal hinge. What is internal hinge? The moment m sub b palm is 0. If the moment m sub b palm is 0, you just consider this on the b palm. Okay, and you also have the elastic weight like this, right? And you have what? You have this one of a sub y palm, and you have also to take the moment here. So this one gonna be m sub b palm, in which equal to 0. So you can determine a sub y palm easily. Okay, it's gonna be something like this. After you know a sub y palm, you will find the m sub d palm later. Okay, if you understand that, just take this one out. Okay, we draw this to determine a sub y palm by taking the moment at this point. Okay, so what is this? This is going to be 1/2 of the distance from a palm to b palm, which is 6, and time what? Time this one. Okay, 1/2 of 6 times this one. And then if you take the moment here and takes this one as positive, a sub y palm gonna time 6 meter, and this one gonna time 2 meter. So we have a sub y palm time 6, and 1/2 of 6, this one time this one is 2, and you have a sub y palm of 4.5 EI. Okay, so you draw the author. This one is 4.5 divided by EI, and then you cut this one by half of the length of 3 meter. So since this one is 4.5 divided by EI, so half of this is going to be half of 4.5 is 2.25 divided by EI. Okay, also talking about this, theta A is the counterclockwise, and you may see from the previous picture if you like. That is going to be theta sub A. This is going to be theta sub A. This one. Let's erase this one to make it clear. Okay, this is going to be the theta sub A. Let me check. This is going to be the theta sub A that we just guessed, and now we are going to determine this for delta sub D. Okay, if you understand that, just taking the moment at D, and then this one gonna rotate. This is gonna be positive. So what we have is taking the moment at this point, m sub d palm will plus with this one. So this is 3 meter. This is going to be just 1 meter. This is going to be 1 meter. as I tell you, one half of this one times 3. So this times 3, and then it's gonna be in the same direction as m sub d prime, and when you reverse this, it's gonna be negative, and 4.5 divided by e times 3. So you get this of 10.125 is upward. Okay, it's upward, it's positive, it's upward. And that's all we have for the example. It's going to be one of the easy one, and you may need to go back and review how to determine the deflection or the slope or both from the conjugate beam if you like. Next, we move to another problem with 2 degrees of indeterminacy. When the problem, this one has a sub x and a sub y, b sub y, c sub y, and d sub y. So the total unknown here gonna be 5. And then we have three equations for one free body diagram. So our degree of indeterminacy is gonna be 5 minus 3 is gonna be 2. That means we're going to need to have 2 redundant. Okay. Again, to make the beam as the simple beam. To make the beam as simple beam, we're gonna take the b sub y and c sub y as the redundant. Okay, take it as redundant to make it as the simple beam. And you also go back and use the principle of superposition. We can separate this beam into 3 beams. One is primary beam, another one is the primary beam subjected to the applied loading. Another one is the beam that's subjected to b sub y, the second. And the third, the beam that's subjected to the c sub y. Okay, this is the primary beam. This is, okay, the primary beam is here. You take all the redundant force out. Only the applied force apply here. And then we interested at the point of B for the compatibility. And also on this one for the compatibility, the delta here is going to be 0, and also here is going to be 0 if we don't set any sentiment into the support. Okay, and then it's going to plus the beam subjected to the force at the B, and this one have the deflection delta sub B due to the applied force, and this one has the delta sub C. For you put b sub y here, the deflection here gonna be b sub y, and then it's gonna times the deflection due to 1 unit force. Okay, over here you're gonna have the deflection, important to specify that, the beam subjected to the redundant b sub y. The deflection here is the deflection at B due to the force applied at B. Okay, and also at C. We also the deflection at C due to the force applied at B. This is important for this. Let me put this one at the same color of purple. Okay, and then we have to put one more by the principle of superposition for the beam subjected to the redundant of C sub y. Okay, and then the deflection here, when the C sub y is 1 unit, the deflection at C when the force applied at C, and this one deflection at B when the C sub y applied at C. Okay, and this one will be in pink, and this one gonna be in the red. And then we will have 2 sets of the compatibility condition. One is at B, okay, another one is at C. Okay, and let me put this one at B. They are going to sum to each other. This is going to be 0. Okay, this is downward is positive. Okay, and downward is positive, this one, and this one also downward is positive. And the other one we have into this. So this one is delta C. This one, oh sorry, this one is 0 first. This one is 0. This one is delta C. This one is plus. All of them is downward. So let's set is plus. Now, the next step is if you determine all the deflection, you will solve the problem. So we need to find the deflection 1, 2, 3, 4, 5, and 6. But luckily, based on the Maxwell reciprocal theorem, F sub CB will equal to F sub BC. So the total we are going to determine 5 deflection. Okay, now start by the primary structure. So you can determine the delta B and delta C. And then the beam subjected to lindent B sub Y. And then the beam subjected to lindent C sub Y. And then based on the principle, Maxwell reciprocal principle, these two going to be the same. We're going to go to the lab and we also can do the test for this, and we can show these two values are equal. And then we substitute this into the compatibility condition at B and C. And now we solve the simultaneous equation. We got the B sub Y and C sub Y. When we got the B sub Y and C sub Y, then we can find the reaction. Okay, the rest of the reaction at A and at D. We can find A sub Y and D sub Y. When we find the A sub Y and D sub Y, we can draw the shear diagram and moment diagram. And then by the moment diagram and the support, we can draw the elastic curve. Okay. Okay, let us consider this beam. Okay, as before, but this beam is kind of a special one with this settlement of 0.01 meter. Let's just change it at point B. So this is gonna be the downward settlement. Okay, and this is no settlement. That means this deflection is 0, but this one is 0.01. And they said the E is 200 gigapascal, I is 175 10 power 6, and if you do the unit conversion in meter, this is going to be 179 10 minus 6 meter power 4. Now, as before, we like to put the beam into the simple beam. So we're going to set the C sub Y and the B sub Y as the redundant D-A-N-T, redundant force. Okay, by doing this, just put the redundant force as the B sub Y and C sub Y as before. Now, based on the principle of superposition, okay, we will separate the beam into 3 cases. One is the primary beam. Okay, another one the beam subjected to B sub Y, and another one the beam that's subjected to the C sub Y. And then we consider the deformation of the beam, and then we set up the compatibility condition. Okay, principle of superposition. We have the primary beam here, and plus the beam subjected to B sub Y, and plus the beam subjected to the C sub Y. And then we do the compatibility equation, okay, at point B and point C. Okay, and then we have this for the point B. We just draw this, follow this. This is gonna be 0.01 meter. We have the deflection here is a downward. Delta B is over downward, right? Delta B is here. And then B sub y F sub BB. And then C sub y F sub B, deflection at B by the force at C. And then another set. Okay, you may have this one. For instance, this one is 0. And this one is delta C. And this one is B sub y F sub CB. And this one is C sub y F sub CC, the last one. And if you saw this, you got to determine the load displacement relationship first. Okay, load displacement relationship first. You may use the deflection table to determine the deflection, or you may use the conjugate beam. Now, since it's really complex one, just use the deflection table. For the deflection table, it's kind of opposite. Okay, this beam have the force that can be act at the point A from the left hand side, and the equation that's used will be used only for this portion from 0 to A. Okay, but our beam, this beam cannot follow that because the force applied here. By doing this, you got to reverse what we have. So the distance from the force to this end, this is going to be, so this one, we're going to set this one as the B. And if you may recall, this one going to be 2.5 meter. This one is 2.5 meter. So the B is going to be 2.5. Okay, this one is 4 meter. This one is 4 meter, right? So the A is going to be this one. A is going to be 10.5 meter. Now, the direction of the X now is in the reverse. So if you like to find the B, this is going to be the X for the deflection SB is going to be 8 meter. Okay, and if you determine SC, this is going to be X sub C, that is going to be 4 meter. Now, you can determine the delta sub B and delta sub C based upon this equation, in which P is 10 kilonewton, B is just 2.5. Okay, X is depend, X sub B or X sub C. And this is going to be 13 meter for the L. Okay, B is 2.5 and X vary. Okay, by basis on this, you just need to follow what we have. B. Let me do the elastic B 2.5. Okay, and A is 10.5. Yes, A is here. Okay, and L and X is 8 meter. So the delta sub B is going to be 7, 10, 2.5, and just vary the X. And 6 EI, L, this is B, and this vary the X, the delta sub B. For delta sub C, just vary the X into 4 meter. Just vary the X into 4 meter. Just do the same, but change this 4. So it's going to have this one for 188.141. Both of them going to be the downward direction. And is this make sense? The delta sub B larger than delta sub C. Yeah, this just makes sense. And the author come to this problem. The same thing we do again, but this time the B is going to be 5 meter. The A going to be 8 meter. Okay, the P will change to 1. This will change to 1.0. Okay, B now change to 5 meter. L still the same, 13 meter. Okay, X is depend. Okay, one is 8 meter, another one is 4 meter as before. So just put into the equation, F sub BB is here, F sub CB also bases on the same but change. Okay, 8 to 4, they also going to be the same. Okay, just change this one, and we will have delta sub F sub BB larger than F sub CB since the force is at B. Now the last one is the delta sub C. This time the B change to 9. The A is 4. Okay, this is 5 plus 4. And then the F sub BC and F sub CB are the same. You don't need to do the calculation. Just put for the F sub CC. Okay, and this one is the force P, and then this is a B is here, 9 meter, and this one the X is this. You measure from here to here, this is the X. Okay, this is the L, and the B and the X. You got F sub CC of 32.231. Okay, and then we put all together for the first set. And this set is important because there is the settlement at B of 0.01 meter. So this is going to be 0.01 meter, and all of them is downward is positive. So what we have is the first equation like this. Next, just put them together and rearrange equation. Next, for this one has the 0 is here, and put everything into here. Okay, you got this equation, and you can solve it if you have the good calculator like a FX 9000 series or FX Casio FX 8000, Casio FX 9000, or even the algebra. You can do the calculation for this, and don't forget about the EI. Okay, put the EI, and then you got the B sub Y and C sub Y like this. Okay, you draw this as a free body diagram, and then you may determine the A sub Y and determine the D sub Y. The A sub X is 0. Okay, now what we have is the A sub Y and D sub Y, and you can do that by yourself. You just pause this one and just take the moment, you get the A sub Y. Summation, moment at D equal to 0. Okay, you get the A sub Y, and then you do the summation F sub Y equals to 0. You got the D sub Y. Now you can draw the shear diagram, you can draw the moment diagram, and from the moment diagram you can see this portion is positive, this portion is negative. You get this one for the inflection point of 0 moment. So this one is going to be the inflection point, and this one is concave upward, this one is concave downward. So if you draw this one, it's going to be like, take this one like this, and this is going to be the deflection of 0.010 meter, and this is going to be inflection point, and then this one going to be this one, and you may draw this one inflection point here. Okay, and also if you like, so this portion mostly has the reinforcement like this. This one has the main reinforcement like this. That is going to be the elastic curve and also the reinforcement pattern, as you may put. But usually we didn't prepare for the settlement. And the moment due to the settlement is going to be very large. Most of the time when we have settlement, we will see the crack of the structure. Okay, another example coming to this. Actually, this one has the fixed at A, so we have A sub x, A sub y, and the moment M sub A. And also at B, we also have the B sub x, B sub y, and the moment M sub B. So we seem like we have 6 unknown, and we have 3 equations. So this one has the degree of indeterminacy equal to 3. But again, we have what? This one going to be 0, and this one also be 0. So in reality, our degree of indeterminacy gonna be 4. Okay, just have this 1, 2, 3, and 4, and minus 2, because we use the summation of x sub x equal to 0 already. So this problem will be the problem with 2 degree of indeterminacy. And this beam is symmetric. Okay, fixed end beam is symmetric. So actually, under the application of the force, this beam will have balance or symmetric. You may use your ruler and bend it. Okay, it's going to bend. So we have the same deflection, and it's going to be like this. Okay, this one going to have very similar shape like this because it's symmetry. Okay, and it's reduced to 2 degree of freedom. So you're going to set 2 redundancies. Okay, if this one you set M sub A and M sub A and M sub B as the redundant. So this fixed support will change into the pin and roller and make the beam into simple beam. Okay, by putting these two as the redundant. Okay, the fixed end change to the pin. Actually, both pin, but to be simple, make it the pin and roller because the A sub y is 0. So this one is pin. Okay, this one is a pin and has the M sub A and M sub B as the redundant. And on the PowerPoint, they set the M sub A and M sub B. I would like to note that the M sub A and M sub B here is in the opposite of what we should have. Okay, so if you make the direction of the redundant wrong, when you calculation, the result will provide you the opposite direction. Okay, so don't worry about that. The same thing occur at this point when we determine this. Actually, when we saw this, our B sub y and C sub y will go to adjust its direction. So beware about it. Okay, so next, compatibility condition. We're going to separate the beam into 3. One is the primary beam, the simple beam subjected to the moment, and the other one, the simple beam subjected to M sub A, and the last one, the simple beam subjected to M sub B. Okay, for the primary, this is going to be theta sub A. For this one, M sub A, if M sub A is 1, this one going to be the alpha at A due to the m sub A applied at A. M sub A equal to 1 unit applied at A. And this one gonna be alpha at B when the moment applied at A. Okay, this is to be this. And since the MA is unknown, we're looking for it, so we term it by the M sub A. The same as open here. This is applied at B. So the slope at B, okay, due to the moment of 1 unit applied at B. This is going to be the slope at A due to the 1 unit applied at B. Okay, so you need to be very careful on the symbol we are going to use. And then what we have on this, that means we're going to determine all the deflection for this size. It's going to be include what we have here. 0 is here, theta A is here. All of them is going to be clockwise. Okay, this one is here clockwise, this one also is here. All of them are plus. And for the other, okay, on this side, this side, this side, and this side, all of them are counterclockwise. So this is going to be counterclockwise. All of them are plus. Now we're going to determine the force, the moment slope relationship, the moment and slope. And 6 of them, since this one and this one will follow the Maxwell reciprocal theorem. So the 6 slope equation gonna reduce to 5. Okay, the first one, we have this picture, the theta sub A. Actually, the theta sub A and theta sub B gonna be equal, right? Because the beam is symmetry, so they are equal. WL cubed over 24 EI. And then we will have this picture. Okay, and for the first one, this one is going to be m sub A equal to 1. So this theta 1 will have to be alpha at A and the moment applied at A. This is going to be alpha at this one as B and the moment applied at A. Okay, and the same thing for the beam here. Now the moment m sub B equal to 1 apply here, and then what we have is the elastic curve here. So this one alpha at B okay, at B when the force applied at B, and this one gonna be equal to this equation when this one equal to 1, and this one gonna be alpha at A when the moment applied at B. Okay, this one gonna be the same as this one. Now we can do the calculation of this easily. Okay, and then we have this one for L over L, you may see the L over 3 EI, and you may not need to consider this side because we can see from the elastic curve. Okay, and then we have this one, we have this one, and we have this one, and alpha sub BA and alpha sub AB, they are going to be equal. Now you put them into the equation, these two, and you may eliminate EI in this case. Okay, and do the what's so called the symbolic analysis. You may use the program like the MATLAB, okay, or Mathematica, okay, or Mad Cat, okay, to solve this kind of symbolic analysis. This is what's so called symbolic analysis. Today we have a lot of program to solve this, or you can use the Maple, okay, to solve it. You solve simultaneously, you will get this one, and I believe there's going to have the negative side for this because all of them is positive, so this is supposed to be negative. The PowerPoint should be wrong. Okay, so the solution of this going to have this direction of the moment, and then you may determine the reaction of WL over 2, and then you can draw the shear diagram, you can draw the moment diagram easily. Okay, and then you can get the elastic curve. This is going to be concave upward, this is going to be concave downward, and if you get hit, for sure this one fix, this one fix, like I said before, and then this one going to be in symmetry. Okay, this one also be in symmetry, and this one is concave downward, and this one is going to be the concave upward. Okay, and then you have this, and then you may also use this to reinforcement here. If it's the reinforced concrete here, this one supposed to be reinforced here. Okay, this is the what's so called the inflection point. This is called the inflection point. So now you can sketch the elastic curve, and you also putting the reinforcement pattern into UP. Okay, you go back and try to work on this. I believe you guys can do it, even though it is the 1 degree of indeterminacy or 2 degree of indeterminacy, and I don't think we can do manual calculation for the 3 degree of indeterminacy. That is too tough on this. Okay, the Maxwell Reciprocal Theorem. Maxwell Reciprocal Theorem is very important theorem. We are going to use this Maxwell Reciprocal Theorem to draw the influence line diagram of static intermediate beam. We are going to study this in the structural analysis. Okay, and this can prove by using the substructure if you like to prove it, but I'm going to show you in short. Okay, if the beam subjected to 1 unit load, okay, the beam gonna defect at B with the force at pi at A, and if the beam subjected to the load at B, and then the deflection will be at A due to the load at B. Okay, and you can prove this one and this one are equal, and then you may say something like this. Don't remember this kind of word. I suggest you to just draw the picture and try everything, explain it by yourself. Again, for the moment, if the beam subjected moment at A, what is A? The deflection at point B due to the unit moment at A is theta sub BA. And if it's subjected to 1 unit moment at B, the deflection at A due to the moment at B, they are going to be equal. You may use the experiment to check this also, not only use the substructure. And the last one is special one. if you put the 1 unit force, cause the slope at B due to the unit force as A, and then you put the 1 unit moment at B, the vertical deflection at A due to the moment at B, they are equal, but they are going to be different in unit. Okay, the slope going to be in the radian unit, but this one going to be in meter or in millimeter, but the value going to be the same. Okay, another thing, when we have the beam, okay, like this, we have one equation minus or partially is okay, f sub bb and b sub 1. And when you move into a more complex problem, okay, now you have two equations. For the problem with the degree of indeterminacy equal to 1, we have one equation. If we have degree of indeterminacy equal to 2, we have two equations. So if we have 3 degree of indeterminacy, we're going to have 3 equations. So if you have n, okay, degree of indeterminacy, you're going to have n redundant force, and then your equation going to be n equation. You're going to solve for n redundant force. So in the form of matrix, you may write it like this, and then is the basis for the development of the matrix structural analysis, and is the basis of the computer programs such as the Suranaree. Okay, and the important thing is we're going to study this in the structural analysis, and you will see that the matrix going to be symmetric matrix. So this matrix can be inverse, okay, inverse to solve the simultaneous equation by solving this simultaneous equation by using the computer. So the structural analysis is going to be a lot easier than previous days that we have. Okay, and it's also the main development of civil engineering nowadays by changing from this hand calculation into the matrix form and put it into your computer and write down some specific equation. So sorry, specific program that we are conveniently use this today. Okay, the last portion of this clip, we are talking about the moment diagram, and I like you to recall when we are very young studying in static. We have the simple beam subjected to the point load. So we have the shear diagram like this, and we have the moment diagram like this. So the point load gonna provide the moment diagram with the linear, okay, linear with linear shape. However, if you have the same beam subjected to uniformly distributed load, your shear diagram gonna change to linear, and your moment gonna be a kind of quadratic function. Okay, that is going to make it very good thing that you supposed to observe on this. Now, by mistake on this, so if the beam still statically indeterminate, you may have the moment here of 0 because there is no external moment, but the moment at the internal support is going to provide the negative moment, and the moment at near the middle of the beam going to provide the positive moment. So by doing this, and you go back to consider the way we place the reinforcement. So this one gonna have reinforcement like this. This one gonna have reinforcement like this. This is spatial reinforcement we got to put. Okay, and this one gonna be, oops, sorry, this is wrong. This is long. This is long. This is long. We're going to put in opposite direction. Okay, this is plus. So when it's plus, this one gonna put it in this one. Okay, if you have the beam like this, like this, and this is gonna be the column, maybe sometime. This is the end of the beam. Okay, this is going to put something like this. You got to put some beyond the inflection point to make the development link like this. Okay, and for the uniformly distributed load, the moment going to be the curve. Okay, and since this one has no external moment, it's going to be zero. And you in combination, the portion that's subjected to the point load going to have linear. The portion that subjected to uniform load is going to be the curve. And if the support change from the pin or roller to the fixed support, they're going to have the moment here. So this is the conclusion. Pin and roller support at the end has zero moment. Okay, also the internal hinge. And fixed support and internal pin and roller gonna have some moment. And the point load produce linear moment diagram with constant slope plus and minus. And the last one, uniformly distributed load gonna produce a curved moment. And the slope gonna be dm by dx equal to v. So this is the end of the introduction to the consistent deformation for the analysis of statically indeterminate beam. And next clips I will show you, demonstrate to you how to solve the problem by manual calculation. I suggest you guys to practice a lot by hand calculation. Also, you may use the substructure to check your results. The result from hand calculation and from the substructure must be equal. It may be a small difference, but most of the time the small difference are small enough to let them to be equal. Okay, that is the end of the method of consistent deformation from the beam. And next we are going to go to the method of consistent deformation analysis for the frame. Now, this is the end of this clip.